So my name's Nick Rosser. I'm a professor of physical geography at Durham University in the UK. And today I'm going to be talking about 4D monitoring of actively failing coastal cliffs using LiDAR. Before I start, I'd like to acknowledge my co-authors, in particular Matt Brain, my colleague from Durham, but also a couple of our former PhD students, Ignacio and Jack Williams, who have done much of the work that underpins what I'm going to be talking about today. I'd also like to thank the organiser of the workshop for the invitation to talk, and hopefully this will be of interest to many of you out there. So in my presentation today, I want to focus on the erosion of hard rock coastal cliffs via the process of rockfall. So the erosion of hard rock cliffed coastlines has typically been monitored using repeat sequential aerial photographs or historical map data, trying to delimit the position of the cliff edge through time and from that derive an erosion rate. One potential problem of this kind of approach is that the processes in action and the changes that are experienced on the cliff face itself are essentially invisible from this aerial perspective. And so to some degree, our understanding of how cliffs change and why and what controls this might have been influenced by the way in which we've monitored them. Now, one approach to tackle this kind of problem has been the adoption of more recent 3D monitoring techniques. And I want to give a very quick overview of the recent gains that have been made through this kind of approach. I then want to focus more specifically around adding a high resolution temporal dimension to these 3D monitoring approaches. So what happens if we monitor cliffs at a very high frequency? What different kinds of insights can we gain? And I want to present three forms of results that we've generated from doing this over the last few years around our understanding of the magnitude frequency of rockfalls from coastal cliffs, the timing of erosion, and also the controls, perhaps sometimes surprising, on when these rockfalls happen and therefore potentially why. So, coastal cliff erosion, our understanding and our modelling of future changes is commonly based on past variations in the mapped cliff line. And the data set displayed at the bottom of the slide here shows a couple of kilometres of coastline from the North Yorkshire coast in the UK, where we have a cliff which ranges from 35 to 70 metres in height. And the coloured lines there show 4 epochs of mapping data that have tried to identify the position of the edge of the cliff, from which we have an erosion rate of about 5 centimetres a year. This kind of approach tends to average out finer scale changes. It's also very insensitive to changes which happen on the cliff face but don't impact the cliff top itself. And as a result, the processes of change across the cliff face are not really well reflected in the cliff top position. Models that use this kind of data are also very sensitive to uncertainties in these measurements because they're multiplicative. So small, poorly constrained erosion rates, when multiplied through these models, have a very big impact on future predicted positions of the coastline. So an approach to try to understand these cliff faces a bit better has been to use 3D monitoring using sequential, either terrestrial laser scanning, so a form of LiDAR, photogrammetry, or more recently structure from motion imagery through photography. This provides unprecedented detail on the rockfalls themselves, their spatial distribution, pattern and evolution, and also their 3D geometry from which we can derive volumes and magnitude frequencies. So the example on the right-hand side shows 2 digital elevation models captured using laser scanning. These are then subtracted to give an image such as that at the bottom. So this is a section of cliff, it's about 70 metres high. The red areas are areas that have fallen off via rockfalls, and the blue areas are areas which have experienced some kind of change, which might be bulging out. If you were to do this every week or every month, you perhaps gain an insight into the seasonal response of the cliff to changes in the weather conditions or the nearshore wave climate, for example, and you might get some indicator of the precursors of what happens in the lead up to some of these events. But what remains challenging is really understanding the controls on when each of these individual rockfalls occur, and therefore what is it that drives changes in rates or changes in the susceptibility of the rock face to collapse. This is because the monitoring frequency often does not reflect the environmental variability. So we know, for example, the wave climate, the tide cycle, weather conditions change actually quite quickly, often on an hourly or diurnal cycle. And so ideally we want our monitoring frequency to reflect that, and we really need that to be able to attribute any direct cause and effect relationship. As a result, our estimates of erosion are still using this sequential approach of, say, weekly or monthly monitoring, the sum of changes rather than individual events. And as a result, our understanding, I would argue, is limited to seasonal versus instantaneous responses, and we can't really tease apart external controls, say the weather or the wave climate, versus internal deformation driven by, for example, weathering. So time really is important here. So we now have these beautiful 3D data sets of our cliff faces through these nice new monitoring techniques, but we need to be able to overcome the problems of time averaged erosion data in order to be able to identify triggers and the actual mechanisms of erosion in order to assess the vulnerability of our hard rock coastlines to future changes in climate or sea level, for example. So we have data sets such as this, which is the distribution of rock falls across a cliff face over a set period of time. But ideally, we want to be able to attribute each of these rock falls with some kind of information about the time when it actually occurred. That allows us to understand the effect of, for example, changing our monitoring frequency on our understanding of the magnitude frequency of the rock falls themselves. It helps identify actually what drives erosion, and it also helps with some quite practical stuff. So, for example, when is the safest time to take your dog for a walk along the beach? Or more directly, okay, what is actually the frequency or the exposure to rockfall on a coastline such as this if we have very high frequency data? Okay, so I'll take you to our field site. This is Whitby on the northeast coast of the UK. This is a section of coastline that actually faces northwards, and we're interested in the cliff face highlighted in the box. This is an actively eroding cliff face. It's about 70 metres high, cut into interbedded shales, sandstones and mudstones. The nice thing about this site is the relative position of the pier, and specifically this lighthouse on the end of the pier, which offers us a vantage point to look back onto the cliff without really interrupting the nearshore wave climate or the cliff face itself. So if we go down and stand on the pier, this is what the site looks like. The lighthouse on the left, where we have our monitoring equipment, and the cliff face itself on the right hand side. And you can also see Whitby Abbey just on the top of the cliff there on the right hand side. So in 2015, we developed a system that was installed in the top of the lighthouse, which was positioned about 350 metres from the rock face itself. This included a Regal terrestrial laser scanner sat behind a window that scanned. It can scan up to every 10 minutes and every 20 minutes, but in the data set I'm going to show you it scans about every hour. It's georeferenced with targets distributed across the cliff face that also allow us to conduct an atmospheric correction. And so the data we collect ranges from around 1 to 5 centimetre resolution, with each scan that it captures being almost 2 million points. We have some control software that streams the data live to the cloud, which we can download almost in real time, and it's also supplemented by a set of weather stations and sensors on the cliff face. So the data set I'm going to talk about is hourly scans, also some thermal imagery, which I'll come on to later, and some weather data. So this is the kind of view that the scanner gets. And the top is a photograph taken from the lighthouse, and the bottom is an image of one of our digital elevation data sets that's captured each hour. And as you can see, there's quite high resolution and pretty good coverage across the cliff face, even though we're not perfectly nadir to the cliff face itself. So the data has some pros and some cons. It's very high spatial resolution, it's very precise, and the frequency is very regular with predictable uncertainties. Unlike some of the more image-based monitoring, such as structure from motion, as an active sensor, the LiDAR works 24 hours a day. It doesn't need daylight to operate. The downsides, it's a single viewpoint onto a complex 3D surface, and so inevitably there is some variability in the point cloud density, and there is some occlusion where we can't see round kind of small edges and corners on the cliff face. But overall, it's pretty good coverage. We developed a workflow, and this is reported in a paper that was led by a PhD student Jack Williams back in 2017, where we take the data from the scanner, we do a set of geometrical transformations to align that data set to the previous one. And then we undertake a 3D change detection from which we derive an inventory of rock falls or differences that have fallen from the cliff face. One note on the data retention pipeline. So even though we collect a lot of data, so over here a period of about 3 years, we've got 20,000 scans or just over. By the time that's gone through our workflow and a series of quality checks that look at each scan, we actually lose quite a significant portion of the data, here around 25%. Much of that is because of inclement weather, where very heavy rainfall, snow or fog means that actually the laser can't penetrate the atmosphere and reach the cliff face, so we don't get a measurement. So we do lose quite a lot there in the process. Even though we've collected a lot of data, we are losing around 5,000 scans, around 25%, that are good enough to do some kind of change detection upon. So this is a view of what the kind of data we're generating looks like. This is a video showing a 9-month period going from March through to December. Each of the coloured areas on here are rock falls that have been monitored to fall from the cliff. They range from things the size of a coffee cup and upwards, and the colour indicates the days since the start of this monitoring campaign. And what you notice is there's some interesting patterns. Not everything is concentrated at the toe where the waves eat away, but they're distributed across the cliff face. You also see some splashes of colour at particular points of time, reflecting potentially individual storms or conditions that lead to rockfalls. And as we go into the reds and the oranges towards the end of the monitoring period in the winter, perhaps the rate of rockfall becomes more intensive. So we can use the data that we've generated to ask some questions. So the first thing I want to look at is rockfall magnitude frequency. So this is a widely used technique from which you can derive the erosion rate on rock faces undergoing discrete changes, such as rockfalls. So on the plot here, we've got rockfall volume on the x-axis on a log scale, and we've got normalized frequency. Sometimes this is some measure of probability on the y-axis, and again, that's a log scale. And the graphs that we've got on this line are negative power laws fitted to subsets of our data. And the subsets have been sampled at different temporal frequencies of monitoring. So the dark blue is every hour, through to the red, which is sampling every scan, or the scan taken every 30 days, or every 3 months. And what you notice is the form of that line changes depending on how frequently you monitor the cliff face. One way to simplify this is if we compare the end numbers. So if we monitor every hour, we get the blue data. If we monitor every 3 months, we get the red data. So clearly how frequently you monitor the cliff face has a big impact on the form of the magnitude frequency relationship, or the probability of rockfalls of different sizes, quite significantly. So on the blue data, there are relatively low probabilities of big events compared to in the red data, where there's a relatively high probability of big events. And that difference is because in the high frequency data, actually those big events are the sum of many, many small events, and we're just counting them in a different way. If you take the gradient or the power law scaling exponent of those lines, and look at the relationship between that and the scan interval, so how often you monitor the cliff, you see an interesting relationship which perhaps gives us an idea of actually what's the optimum frequency with which we should monitor the cliff. So the circle data here is the power law scaling exponent, and what you notice is for scan intervals less than 100 hours or 4 days or so, the more you measure it, the greater the power law scaling exponent. So your power law form changes. But interestingly, above, for scan intervals longer than 100 hours, actually it makes no difference. So you could go back every 4 days, every 4 weeks, or every 4 months, you would get the same magnitude frequency distribution. So this gives us an insight into what's the optimum frequency if we want to understand the magnitude frequency relationship for any individual location. So the form of this would change depending on which cliff you were looking at. So does monitoring frequency matter? Yes, it absolutely does, if you want to use magnitude frequency of rockfall or erosion events that result from those to calculate erosion rates, for example. The other thing that's interesting is the form of these magnitude frequency relationships, and they have 3 distinctive patterns. The first is a mid-range size of rockfalls that adheres very well to negative power law. So between the two horizontal dashed lines, we get a very good fit to a negative power law relation, which is good for modelling erosion rates. We also get a roll-up for the smallest rockfalls, and this is interesting because that's converse to many data sets that are similar but captured at a much lower resolution of monitoring. And that, to me, implies that we've got another process going on here, perhaps the deterioration and crumbling of the cliff face, which we're capturing. And we also have a heavy tail, or a higher frequency of the biggest events that we're monitoring. So the second result I wanted to show you was about the timing of the rock falls and when they occur, and what is it that drives the overall accumulation of erosion of the coastline. So here we've got a couple of graphs showing the erosion from 2017 through to the end of 2019, so a period of 3 years. And in the middle plot, we've got the cumulative erosion, or the cumulative rockfall volume, shown in the black line, and then total rockfall volume subsampled over a weekly interval during that period. What you notice is there are two things driving the growth of that curve. So one is large event, the steps in the black line, and the second is iterative erosion. So here we're defining these large events as things with a rockfall component that's greater than 1 cubic metre. The biggest event that we recorded during this period was 22 cubic metres, and the smallest was 0.02 cubic metres. And in total, we lost about 180 cubic metres of rock over this 3-year period. It's notable here that the large events, so the bigger rockfalls, occur both in the winter, the spring and the summer, and especially after summer storms. If you look at the long-term erosion rate that you derive from this data, it's about 11 millimetres per year. So it's way smaller than the precision of many of the mapping techniques that we use based upon aerial photography, even airborne LiDAR, or even historical maps. The other component of this long-term erosion rate is this background iterative erosion, which is the gradient of the line in between these steps. And interestingly, this is about 4.6 millimetres per year. And in total, that contributes to around 42% of the overall erosion of the cliff. So it is significant, this background almost continual mass wasting. Large events contribute about 60% of the overall erosion. And if you look at the graph at the bottom, the percentages there show the relative contribution of the single largest rockfall to the loss of material in that event. Commonly, these large events are single or are dominated by single rockfalls. So interestingly, we've got both big events driving one-off changes, but also this iterative background erosion. And so what controls these two processes and what's significant in driving this background rate versus these one-off single failures is really interesting and is important to get a handle on if we're to understand future responses of cliffs to, say, climate change or sea level change. The final aspect I wanted to talk about was the ability to use this data to look into the controls on cliff erosion and cliff collapse, and particularly here taking advantage of the fact that we're now collecting the erosion and the rockfall data at the same frequency with which we normally collect, say, weather data or wave data. Now, one particular recent interest, at least in the UK, has been the apparent association between periods of very hot weather and cliff collapse, as is seen in these extracts from the media from a couple of years ago, where it was noticed that there were several significant cliff collapse events coincided with periods where we had very warm weather. So we have the potential here to look at the association between the temperature, or more specifically the cliff surface temperature, and whether we get more rock falls. So to do this, we've developed a system that runs in parallel with our laser scanner, here using an infrared thermal camera, positioned again within the lighthouse with an accompanying control system that captures a thermal image every time the laser scanner collects a 3D scan, and then again posts it to the cloud. The kind of data that this generates is really quite interesting. So this is cliff surface temperature measured at 1 hour resolution for the period of a whole year. And so each of these images shows some summary statistic of that data set, where we have a stack of all of those thermal images And in the top left, for example, we're looking at the mean temperature. So each of those pixels is the mean of 365 days and 24 hours worth of data. What's interesting is here some of the variability, which is perhaps surprising, and note that the colour scales vary across these four images. So if we look, for example, at the maximum, it's perhaps surprising that a cliff on the northeast coast of the UK, the maximum temperatures experienced are in excess of 40 to 45 degrees in some parts of that cliff face. Equally, the minimum temperatures are quite extreme as well. So here, looking at the dark blue colours, some parts of the cliff face experience during the year temperatures as low as -10, 11 to 13 degrees. We can also look at the variability. So in the bottom right here, we have the standard deviation. Or if we actually look at the range in temperature during the year, we see some really quite surprising results. So the blue areas here, the range between the minimum temperature experienced and the maximum temperature experienced during the year can vary between 25 degrees in the blue, but also in excess of 55 or towards 60 degrees temperature variation. And obviously that potentially has significant implications for thermal contraction, thermal expansion, and the creation of fractures and deterioration and weathering of the rock face as a result. We can also think of this thermal data in terms of a time series. So here we've summarized it across the 4 seasons to look at the mean values, the maximums and the minimums, and think about how this corresponds to sunrise and sunset, and periods when the cliff face is warming up, and the periods when the cliff face is cooling down. So in the winter, perhaps not surprisingly, the cliff is cold and it doesn't really vary very much in terms of temperature, whereas in the spring and the summer, the cliff is warmer, but we also get some quite dramatic changes in the temperature with heating and cooling periods with very steep rates of change in temperature, particularly around sunrise and sunset. So what we can do is superimpose this data set with our rockfall data set, which we captured every hour. And some interesting results fall out of this. So again, here we've summarized this by the 4 seasons: winter, spring, summer, and autumn. And what we notice is that rockfalls are 2 to 3 times higher at midnight, sunrise, noon, and sunset. We see significant correlations between both the absolute temperature, but also the rates of change in temperature and rockfall occurrence, particularly during winter and spring seasons. Surface temperature therefore links directly to rockfall, and particularly this is apparent during dry conditions. And these are conditions where that kind of iterative background erosion of the cliff face, which we saw previously, is dominating the loss of material. During sunrise, positive rates of change in temperature, so heating, statistically links to rockfall occurrence, and during sunset, negative rates of temperature change, cooling, linked to rockfall as well. So we have a situation where it's both the absolute temperature and the rate of change of temperature and the direction of change of that rate of change in temperature that's significant in controlling the rockfall. So some really interesting insights. And so I guess going back to the question about when's the safest time to go for a walk with your dog, I'd maybe suggest avoiding sunrise and sunset as a starting point. So to summarize, hopefully I've been able to show some of the benefits and some of the advantages of using high temporal resolution cliff monitoring. We spent a lot of time trying to develop the system to make it robust, but one important point is that data loss can still be high, primarily because of the inclement conditions that we often experience on the coastline. I think it also demonstrates the importance of reporting the design of the monitoring framework, such as the frequency with which a site is monitored, alongside the erosion data that's derived to fully understand the potential limitations that come into play. Our analysis shows a very clear sensitivity of the results that we generate, such as the form of the magnitude frequency relationship to the monitoring frequency itself, but there does seem to be an approach to designing an optimum frequency for any given location. We've been able to look at the relative contribution of background versus event-based erosion, and those two are potentially influenced by different environmental controls, so pulling those apart and understanding those is essential for assessing future change. We've also identified potentially unexpected controls. So there is a very clear association between cliff surface temperature and rockfall frequency. And so there's a lot more work needed to really understand those in an environment which has a very aggressive wave climate, even then these controls are important. So one question that I would leave us with is it actually possible to understand the controls on short-term erosion and perhaps longer-term change without doing this kind of high-frequency monitoring? So I look forward to discussing the results with anyone who's interested, and thank you for listening.